Challenges of classical approach that we face is time frequency domain analysis. So time frequency domain analysis involves time series data by examining the width and height of measured thresholds. Fourier analysis is a common used technique in the frequency domain to analyze the time series data. Discrete Fourier transform and fast Fourier transform are particular methods for transforming a raw time series data into frequency spectra. DFT takes the following form, where x underscore k and the kth frequency value transformed from given input data, which is x underscore t. We learn about the statistical model. So statistical measures such as mean variance, median, quantile, kurtosis, and skewness can be calculated to generate a statistical model for time series data analysis. Also, distance-based models is a common approach used in time series anomaly detection to quantify the similarity or dissimilarity between two temporal sequences. Based on calculated distance, anomalies can be identified if the distances from the normal sequence fall outside the expected range. How can we use distance-based model? So the most commonly used measure for distance in time series analysis is the Euclidean distance. It computes the distance as the length of segment connecting two points in the time series data. Dynamic time wrapping is another popular distance measure used in time series analysis. DTW allows for non-linear alignment between two sequences that may be locally or out of phase. It is particularly useful when comparing sequences with different lengths or when there are temporal distortions in the data. You can use predictive models. A predictive model is a mathematical statistical model that is trained on historical data to make predictions or forecasts about future events or outcomes. These models use patterns and relationships in the data to learn and generalize from past observations, allowing them to make predictions on new unseen data. Clustering model. A clustering model is a machine learning algorithm that groups similar data points together based on the inherent pattern of similarities. The goal of clustering is to identify natural groupings or clusters within a dataset, where data points within the same cluster are more similar to each other than those in the other clusters. There are various clustering algorithms that can be used to build clustering models, such as k-mean, hierarchical clustering, dbScan, k-mean algorithm, and Gaussian mixture models. Challenging issues that we faced are traditional approaches have made significant strides in anomaly detection in time series data, but several challenges still require attention. And these basic challenges that we face is lack of labels and complexity of data. So lack of labels. In many industrial scenarios, failure modes are exceedingly rare, making them inadequate for labeling labeled training data. Collecting sufficient labeled training data is time and resource intensive. Class imbalance between normal and abnormal data further complicates model training. Complexity of data is univariate time series data analysis remaining vital, especially in resource constrained environments like edge computing. As industrial applications become more automated, control systems complexity increases. Large number of dimensions lead to curves of dimensionality, causing performance drops in traditional approach. These challenges underscore the need for advanced techniques like deep learning to tackle time series and anomaly detection effectively. Before starting with the deep learning model that we built, let's learn various other methods that can be used for anomaly detection. So ensemble methods for anomaly detection include these are used to combine multiple models to improve the accuracy and robustness of anomaly detection. Techniques such as bagging, boosting, and stacking are commonly used in deep learning. Ensemble models are also help reduce false positives and increase the detection rate of anomalies. You can also use transfer learning for anomaly detection. Transfer learning is a technique that allows models trained on one domain to be applied to other domain with limited labeled data. Pre-trained models can capture generic features and patterns useful for detecting anomalies. Fine-tuning the pre-trained models on target domain can further enhance performance. Also, we can use online learning for anomaly detection. Learning enables models to adapt and update in real time as new data arrives. Incremental update models can handle dynamic environments and detect anomalies in streaming data. Online learning is useful in applications where immediately anomaly detection is required. Let's start with our model. So deep learning architecture for anomaly detection. We can use various type of architectures to build a model. Basic that we use is recurrent neural networks. RNN can capture temporal dependencies between time series data and local patterns. They are useful in applications where previous data is important in predicting the next. Convolutional networks. CNN models are used in analyzing local patterns in time series data and are applicable in variable length input sequences. We can also use autoencoders. Autoencoders are used in unsupervised learning to capture high level features in time series data and reconstruct the original input. They are useful in applications where no label data is given. These are the various methods and their categorization that we can use for building time series data. Anomaly scoring methods. We can identify anomalies by using these errors. Reconstruction error. Reconstruction error is the difference between input and output data after the model reconstruction. This is useful when we have the correct label data. Also, we can use prediction error. Prediction error measures the difference between predicted and actual output values. This is useful in detecting the anomalies that haven't occurred in the training data. You can use dissimilarity. Dissimilarity measures the difference between normal and anomalous data. This is useful in detecting the novelty of the data in the system. Now, there are various ways to measure the performance of the model that we have built. Basic ways that I have listed down here are accuracy. Accuracy measures the correctness of the model output compared to the true values. We have precision. Precision measures the proportion of anomalies the model correctly predicted among the total number of predicted anomalies. Then we can use recall. Recall measures the proportion of anomalies the correct model correctly predicted among the total number of true anomalies. You can use F1 score. F1 score is the harmonic mean of precision and recall and is used to balance both metrics. We can also use OUC, AUC and ROC curves. AUC and ROC measures the true positive rate against the false positive rate and is useful metrics for unbalanced datasets. Now we will see what is benchmark datasets for anomaly detection. Here I have listed primarily three benchmark datasets. First is Numenta Anomaly Benchmark. NAB is a benchmark dataset for evaluating anomaly detection algorithms in time series data across various industries, including manufacturing, IT, and environmental monitoring. SWAT and VADA. SWAT and VADA are datasets used for anomaly detection in industrial systems, including water treatment and automotive industries. We can also use Yahoo WebScope S5. Yahoo WebScope S5 is a large-scale dataset used in research in various domains, including time series analysis and machine learning. So this lists down the hyperparameters values for each method. In fact, we used five hyperparameters, which is USAT, VTA, GDN, THOC, and LSTM. Similarly, in VADA and MSL, we use various hyperparameters. This is how the model performed. So here we list down the precision, recall, and F1 score for each of the model that we used. Best performance is bold, and the second best performance is underlined here. And now, what are the guidelines of new practitioners? There are various detection strategies such as real-time versus early warning and sliding window versus incremental update. And then there is training and pre-processing techniques that we are going to discuss, which is loss function, batch learning versus online update, and denoising. Real-time versus early warning. So in real-time anomaly response is quick, whereas in early anomaly detection predict and prevent future breakdowns. Data processing process actual anomalies, whereas early anomaly detection predicts and forecasts potential anomalies. Similarly, we have listed down all the differences that are there between real time and early warnings. Both of these have their pros and cons. Now let us discuss about sliding window versus incremental update. So sliding window processes all historical data points within a window, whereas incremental update approach updates predictions incrementally for new data. Sliding window requires selecting an appropriate window size. Incremental update approach suitable for streaming environment. Length of temporal dependencies depend on window size. Maintains a compact summary of past data. Whereas window size just depends on dataset characteristics. Well suited for datasets with dynamic data arrival. Sliding window approach can overlook anomalies with excessive window sizes, more efficient for continuous anomaly detection. Whereas sliding window approach involves larger competition for maintaining the entire data streams. Incremental update approach offers computational benefits and lower memory usage. Sliding window approach limited has limited capability to capture long-term dependencies with small windows, whereas incremental update approach limited support for pre or post processing methods. Loss functions that we used basically that can be used are adversarial loss function, reconstruction loss, prediction loss, and negative log likelihood. Uh, Adversarial loss utilizes adversarial formulation involving a discriminator and generator. Typical use cases are involves modeling capability used in generative models. Reconstruction was utilized autoencoder and similar methods where AE reconstructs normal data well. Preferred choice where AE used for is anomaly detection. Used in prediction loss is used in prediction-based approaches, comparing prediction with real observations. Whereas negative log likelihood estimation is the estimation of log likelihood commonly used in generative models. Now we will compare batch learning and online update. Batch learning assumes a stationary data distribution and requires a new batch of training data sampled from the same distribution of model fine-tuning. Whereas online update supports model fine-tuning with newly appended data without the need to train the model from scratch. Batch learning common in deep learning methods with a batch learning approach may be problematic when data cannot be recollected frequently. Online update HTML-based methods often support online updates. Deep learning methods rarely incorporate online updates due to conventional assumptions about data distribution. Some methods adjust thresholds for binary decision making. Batch learning assumes stationary data distribution, which may not align with real world data. Online update avoids the assumption of data stationarity, but suffers from the challenges of catastrophic forgetting when adapting to new data. Also, online update, a common approach include regularization, dynamic network structures, and memory replay based methods to mitigate catastrophic forgetting. So this would be the end of slide. I hope you understand how to design a deep learning framework for predicting anomaly detection in time series data. Thank you.